Okay, like I did for the AP Stat exam, I'm going to work these problems cold. The questions were released yesterday. Haven't looked at them for the 2023 Calculus AB exam. So I'm going to start with question 1 on section 2, the graphing calculator section. Have a table here. It says a customer at a gas station is pumping gasoline into a gas tank. Rate of flow of gasoline is modeled by differentiable function f, where f of t is measured in gallons per second. T is measured in seconds since pumping begins. Selected values of f of t are given in the table. So the rate, f of t is a rate function. This is 2023. Oops, let's go ahead and do this. 2023 AP Cal exam, FRQs. This is number 1. So F is differentiable and F is the rate of flow. Selected values given in the table. So using correct units, interpret the meaning of the integral. A is the integral from 60 to 135 of f of t dt in context. And use a right-Riemann sum with 3 subintervals, 60 to 90, 90 to 120, and 120 to 135 to approximate the value. So let's go ahead and start with the approximate value. Integral 60 to 135 of f of t dt is approximately equal to the right-Riemann sum. Let's go back to the table real quick. We're going 60 to 90, 90 to 120. So I'm going to go ahead and plot this. We'll call this 60, this 90, and this 120, and this 135. And it looks like f of t is at 60.1, at 90.15, at 120.1, and at 135.05. And so, for a right-Riemann sum on these 3 subintervals, we're looking at this rectangle, and this rectangle as the estimate. So the height here is 0.15 times the width is 30, and the width is 30 again here, and the height is 0.1. And here, the height is 0.05, and the width is 15. So that means this right-Riemann sum approximation is going to be 0.15 times 30 plus 0.1 times 30 plus 0.05 times 15. And since this is a rate function, the integral is an accumulator function. And let's move to part A again. It says we want to interpret the meaning of that. That's the value. So we've got the approximation, and we're going to put units. This is going to be the model where F is measuring gallons per second. So this is going to be gallons. Pumped between t equals 60 seconds and t equals 135 seconds. Oops. So that will be our solution to part A. Part B, must there exist a value of C for 60 less than C less than 120 such that f prime of C equals 0. Justify your answer. Okay? So the mean value theorem tells us that if f of x, we'll go f of t here, is a differentiable function or continuous on our interval here is 60 to 120 and differentiable on 60 to 120, then there exists a C in 60 to 120 such that f prime of C is equal to f of 120 minus f of 60 over 120 minus 60. Since we have f of 120 and f of 60 both equal to 0.1, that equals 0. So yes, by the mean value theorem, there exists a C in 60 to 120 such that f prime of C equals 0. That's part B. Oh, we have to remember, we defined that f is differentiable. Since, we need to make sure and state this, since f is differentiable, f is also continuous. On 60 to 120. 60 to 120. Careful. Okay, we're good. Part C. Rate of flow in gasoline in gallons per second can also be modeled by this function, g of t. Let's go ahead and write that down. T over 500 times cosine t over 120 all squared for 0 less than or equal to t less than or equal to 150. Using this model, find the average rate of flow of gasoline over the time interval from 0 to 150. So the average rate of flow is the average of f of t. So that's going to be average rate of flow is going to equal 1 over 150 minus 0 times the integral from 0 to 150 of f of t dt. I'm going to enter that function in the calculator. Make sure my calculator is set on radian mode. It is. Second quit. Our function is t over 500 y equals cosine, and this is going to be x divided by 120 squared. So x over 500, let's make sure I got the function entered correctly. I'm going to go ahead and insert the parentheses. Oh, it said, yep, I did put 100 instead of 500. So second insert parentheses, change that to 5. So that's a 500 up there. I'm going to insert another set of parentheses here. We can Just do it like this. That's good. And that's x over 120 all squared. So that should be what we need. So the next thing we're going to do is we're going to get out of here. We're going to go to math. We're going to go to function integration from 0 to 150. I'm going to go to vars, y1, where we put the function. We put x in place of t, so we're going to take the integral with respect to x. And that looks like 14.399 gallons per second, because this is the average value of the rate function. So the rate function is measured in gallons per second, so this average value would also be measured in gallons per second. That's the average rate of flow. So using the model G defined in part C, find the value of G prime of 140. So D. This we can find in the calculator. Interpret the meaning of your answer in the context of the problem. Okay, G prime of 140. Let's see. Rate of flow of gasoline gallons per second. Yeah. Interesting why F would be the rate of flow and G would be the rate of flow. Okay, just a different function. So we can find G prime of 140 using the calculator also. Math. This time we're going to do the numeric derivative. And we're going to do the derivative with respect to x. Since that's what we entered in the calculator, we're going to put y1 in here again. That's that function. That's the function g, that's right. And we're going to evaluate that at x equals 140. And so that's going to be negative 0.004 or 0.005. And that's the rate of change. So this is gallons per second. So gallons per second squared. So interpret the meaning of your answer in the context of the problem. The rate of flow in gallons per second is changing decreasing. Let's go ahead and put decreasing. By 0.004 gallons per second squared when T equals 140. That's when the gas has been pumping for 140 seconds. That's part D. And that's the end of that problem. So we're going to stop the video here.